Hello everyone. Now the third part of control system laboratory will be dealing with closed loop system. So name of the experiment is principles of feedback. Now, as I said earlier, the open loop system causes a problem. That is, if the environment in which a certain thing is operating changes, that is, if a brake is applied or if the system finds any hindrance, then the output changes. But we don't want that. We want a constant speed, for example, or a constant position, or whatever we are controlling. So, in order to do that, what we need the information of the output and change the input accordingly. So the process by which we do that is feedback. We take feedback from the output and change the input accordingly. So in your theory, you must have learned by now, you must have seen a diagram like this. Here we have controller. Then after controller, we have our plant. After plant, we have our output. From output, we take a feedback. From feedback, we bring it here and we subtract it. Why do we subtract it? Because it is negative feedback. Now let our input be R. This R minus feedback is our error signal. This feedback, suppose this is H. Sorry, this is F, and let the controller gain be Kc. We know the plant gain is Kp, and let output be termed as C. Now, if this is the case, then what is output? Output C is equal to E into Kc into Kp, E into Kc into Kp. Now, E is equal to, as we can see, R minus F. That is, R minus F is C into H. So, C, H. So, if we do that, what we get is C is equal to R minus CH Kc Kp. From there we get C plus CH Kc Kp is equal to R Kc Kp. Now we take C as common. 1 plus Kc Kph is equal to R Kc Kp. From there we get C by R is equal to Kc Kp divided by 1 plus Kc Kph. So Kc Kp divided by 1 plus Kc Kph. This thing C by R is called closed loop transfer function. You must have learned it from theory already. Closed loop transfer function. So it is also called in short form CLTF. So this is our closed loop transfer function. Now closed loop transfer function consists of two parts. This Kc Kp, this one. This part is called forward loop transfer function, and we have this part Kc Kph. This is called open loop transfer function, OLTF, and this is forward loop transfer function. Okay, so closed loop transfer function is equal to forward loop transfer function divided by 1 plus open loop transfer function. Now, what is the significance of these? What is the significance of this expression? The significance of this expression is that we can modify as C by R is equal to 1 by Kc Kp plus H. So, in general, the value of H is equal to 1 because we generally use unity feedback. If value of H is 1, we get 1 by 1 by Kc Kp plus 1. Now here plant gain is our constant. Plant gain is unchangeable. So what's a variable? The variable is Kc, or the controller gain. We can modify the controller gain. Now what happens is, what do we want? We want the output to resemble the input signal that we have provided. That is, for example, if we look at the first experiment, if our input was 3 volts, our output was not 3 volts. Output was, suppose it was 2.750 volts. As a result, gain was a little less than what we want. So we want the output to be 3 volts as well. We want input and output to be equal. If the inputs and outputs are equal, then what would happen? C by R is equal to 1. In order to make C by R is equal to 1 or very close to 1, what we can do is we can keep these value very close to 1, then 1 by 1 will be equal to 1. If we want to keep this value very close to 1, since we have 1 added here, we want to keep this value as small as possible, and the way of decreasing this value is increasing Kc. So as our controller gain increases, 1 by Kc Kp decreases, and as a result the output resembles more closely to the input. That is, the more the controller gain, the more the output resembles the input. That is one takeaway from this expression. Now, here there is another takeaway. What we can do is, we know E is equal to R minus F, or R minus CH. So from there, what we can do is C is equal to E Kc Kp. So we can find it R minus E Kc Kph. From there we bring it to the left hand side and take E common. 1 plus Kc Kph is equal to R. From here we find E by R, 1 by 1 plus Kc Kph. So in this part of the expression too, one thing that we need to see is, we want our error signal to be as low as possible. So how can we do that? We can do that by increasing the Kc. The higher the value of Kc, the lower the error signal. So in both the cases, we can see, by increasing the value of Kc, or the controller gain, what we're doing is, we're bringing the output more close to the input, as close to the input as possible. Now these equations are there, and again, all this time we have talked about the gain response. We can talk about transient response as well. The closed loop time constant would be Tp divided by 1 plus K C Kp. Now this Tp is equal to the tau that you have measured earlier in experiment 1 and 2, and TCL is the tau CL is the time constant of a feedback system. So we can see that the time constants of the feedback system, what do we want? We want the system to be fast. That is, we want the time constant to be as low as possible. How can we decrease the time constant? For example, why do we want it as low as possible? Suppose if the time constant is greater, the system response is like this. If the time constant is smaller, system response will be like this. So we want this response. We want to reach the output as soon as possible. If we want to decrease the time constant, what we do is, we increase the gain. That is, the higher the value of Kc, the benefit of Kc is, if Kc is increased, our time constant is decreased, and our error is decreased. That is, the output resembles the input more. Now these are the two equations that we have derived. One is tau CL is equal to Tp divided by, I can write it tau p divided by 1 by 1 divided by 1 plus Kc Kp, and another is T by R is equal to 1 by Kc Kp plus 1. So we have mathematically derived these two equations, and we'll now, in this experiment, our task will be to actually verify this experiment experimentally or via, in this case, via simulation, since we do not have the hardware at hand at this moment. So what we can do is, mm, we can we can at first look at our sheet. So the setup that, oh, one thing is there, but the relationship, you see this relationship, this is important. uh, so see, there are two curves. One curve is this, one curve is this. Now, the Kc in both the cases, uh, Kc here is more, Kc here is less, obviously, because the gain here is less, the gain here is more. But as I've claimed that if Kc is more, speed is fast. But you can see that from initial method, the time constant of both are almost same. Then how can we claim that this graph is slow and this graph is fast? How, how can we do that? We can do that because see, the time constant might be same, no problem with that. But in suppose time constant 1 second, in 1 second, the value of the output is this much. Say it seems like it would be 0.6 or something like that. But in 1 second, the value of the output in the blue curve here is 2. So this curve with a higher value of Kc can reach to a value of 2 uh, in the same time that this curve with a lower value of Kc can reach to a value of 0.6. That is, the change in value in this curve is much higher than the change in value in this curve. As a result, this system with a higher value of Kc is faster than this system with a lower value of Kc. And obviously, if you increase the gain, or the controller gain, the overall output will increase and the motor will run at a faster speed than if the controller gain was less. We'll see that shortly in our experiment as well. So now let us go into the simulation mode. So in simulation, we see CA06P05. We have to load that. So we load setup CA06P05. After loading it, we go back to our uh, simulation setup. DC level is 0%, offset 50%, that is 2.5 volts. Wait 10 milliseconds, and controller is proportional. We can see controller is proportional. Offset is 50%, rate is 10 milliseconds. Everything is as it's supposed to be. Now the graph that you see is this graph over here. This is the input, 2.5 volts, and this is the error graph. Error graph is switched on. So error graph is not clearly visible at this moment. It will be very soon. This is the velocity graph. We just match the color of it. And this is the drive curve. If we stop it, you'll see the drive curve. Again, if we stop the velocity, you'll see the velocity curve. This is the velocity curve. Again, if you stop the input, you'll see the input curve. Now, okay. Now these curves are there. So what's important is, what we do is, the first thing that we need to do is, if we look at the data table, uh, go below, we go down and we look at the data table. What we need to do, we first make the gain is equal to, this gain is actually Kc, input voltage is 2.5, planned gain Kp we have determined in experiment 1 and 2. So first what we need to do is, we need to put gain is equal to 1, and we need to find velocity volts, which is the output velocity. We need to find C by R, that is the output velocity divided by input, that is output velocity divided by input voltage, that is this velocity volts divided by 2.5 will give us C by R. Now, what is C by R theory? C by R theory would be, we have a value of Kc which is 1, we know Kp, then putting the value of Kc Kp in this equation will give us a C by R. That value of C by R will be putting in this column. Then we will find the errors. Error is basically equal to input minus this velocity volts, that is this minus this error, and E by R this divided by input voltage, that is E by R. And E by R theory is what we have learned from the expression, that is E by R is equal to 1 by 1 plus KC KP. One thing is to be noted that I'm not writing H. I'm not writing H because, as you can see, this is an unity feedback, unity negative feedback system. So H is not needed. So from the first data table, we will verify these two phenomena, E by R and C by R. So we'll find one value from experiment and one value from theory, that is from this equation, and we'll see whether these both values are equal or not. So let us take one data and see how it happens. So our gain is equal to 1. So what do is we freeze it. Okay. Okay, we freeze it. Sometimes these kind of problems will occur because in simulation mode it's not very polished. So don't be worried about it. You load the setup again. File. Okay. Sometimes it happens that it doesn't work the way we want it to. So file, load setup. We load CA06P05 and we freeze it. After freezing it, we make the timer on. Now our input, if we click here, this is our input, which is 2.5 volts, which is supposed to be 2.5 volts. And the output here, for whenever we are measuring the output, let's do one thing. We turn drive and error off, only output is on and the input is on. We start it again. After starting, we freeze it again. So our input is 2.5 volts, output is over here. So we click here and the output. Now, try to make it as perfect as possible. Okay, output is 1.2 volts. So if we look at here, for gain K is equal to 1, I write it here. For gain K is equal to 1, V well will be equal to 1. Let's check again. 1.2 volts. So V well is equal to 1.2. And next, then what's the next thing? C by R. C by R would be C by R is equal to 1.2 divided by 2.5. If we calculate it, excuse me for a bit while I reach for calculator. So it would be 1.2 divided by 2.5. It would be 0.48. 0.48. According to theory, C by R should have been 1 divided by 1 plus Kc is equal to 1, Kp is equal to 0.92 plus 1. So we make the calculation by calculator. 0.92 plus 1. So it should be 0.479. 0.479. So as we can see that the values matches. That is what we are doing is correct. And again, let's look at since V well, that is since our output V well is actually our C. Since C is equal to 1.2, E is equal to 2.5 minus 1.2 is equal to 1.3. So E by R is equal to 1.3 by 2.5. 1.3 by 2.5 is equal to 0.52. That is the practical value of E by R. And theoretical value of E by R, from this equation we obtain 1 by 1 plus 1 into 0.92. So we get 1 by 1 plus 0.92, 0.52. So we can see that the values that we are obtaining from practical data, that is from graphs, are matching with the values that we are obtaining from theoretical data, that is from equations. So the equations that we have perceived are actually correct, or we have thus verified the equation for gain is equal to 1. So we'll be verifying this same equation for gain is equal to 2, 5, 10, 20, 50, 100. For example, what you'll do is you'll just start, and at first, before we move on, at first you see that the output is very much different than the input when we actually see for the value of Kc, for low value of Kc. So in in the right top corner, you can see that you can see the effect of brakes and everything, and uh, it will be really different when we increase the gain, and actual value of the output velocity will also change when we increase the gain. For example, if I see it in the right hand top corner, what we do is we increase the gain to 10, and see, instantly the voltage output voltage has risen. If the output voltage rises, what you'll see that over here, you'll see that at high value of Kc, the response is better, the response is faster, and the effect of brake is not that as high as that was in case of low value of Kc. So in case of closed loop system, what we're doing is if we actually increase the value of Kc, then we actually get the output as close to the input as possible, and the effect of external element decreases with the increase of Kc. Effect of external elements will decrease with increase of Kc. Now, what happens is we'll fill up this table here and compare our observation with the theory. Next, what we'll do is we'll find the time constant, because if we remember, we had an equation for time constant as well. Now, Kp we know already, tau p we know from the experiment 1 and 2. So if we delete these things, our tau CL is equal to tau p divided by 1 plus Kp Kc. Again, I'm not mentioning H since it's unity feedback system. So in order to measure this, we go above and we change the simulation settings. So what do? We take step input level of 20% and rate of 10 milliseconds. Then what happens? Let's go to the simulation. We make the input step level as 20%, offset as 0. So we have a step response available now at this moment. We have a step response available. Our value of k is equal to 1. You can readily observe the effect of gain, controller gain here. For example, the value of k is 1 and it's giving output like this. So that is, it's very quickly reaching to the final steady state value. If we decrease the value of k to 1, you'll see it takes much more time. So it is very readily, the effect is very readily available. And if you look at the right hand top corner, you'll see that in case of step response at a higher value of k, that is at k is equal to 10, you'll see the effect of braking also. The steady state will be achieved really fast, and the effect of braking would be less. That is, in case of applying the brake, the change in velocity will be low. Now, what do we do in this experiment? What do? We go to the data sheet. So we take gain is equal to 1, 2, 3, 4, 5, and 10. For these 6 gains, we measure the theoretical time constant. What's the theoretical time constant? We know tau p, we know kp and kc. Kc's value will change from 1, 2, 3, 4, 5, 10. So from that, we'll get 6 values of tau cl. These are theoretical time constants. And then we measure the time constant. From where do we measure the time constant? We measure the time constant from here. How do we do that? At first we decrease the value of k to 1. Now we use 64% method to measure the time constant. Then we increase the value to 2. We again use 63% method to measure the time constant. And for all the 6 data, we measure the time constant. We fill out this table, theoretical time constant from the equation to the left, measured time constant on the equation to the right, and we compare these values. And the last part of the experiment is finding the open loop frequency response. Before we go on to that, we just let's measure maybe for k is equal to 2, let's measure the time constant. So what do we need to do is we need to freeze. So for measuring time constant, first thing that we need to do is we need to find out the output span. So we select the top part here. Okay, and we select the bottom part here. Try to align them as much as possible. Okay, so our 0.65 plus 0.65 is 1.3. So our output voltage, output span is equal to 1.3. So our 63% value is equal to 1.3 into 0.63 plus minus 0.650. 0.65. If we do that, minus 0.65 plus 1.3 into 0.63, the value that we obtained is 0.169. Now we go back to our curve. Now after going back to our curve, we find the value where the output is 0.169. We will not get 169, probably we will get so we are not getting anything in the middle of these two. So what we do is we magnify it. We magnify it 2 times, or we can magnify it 2 times, then we start again, or maybe we can magnify it 5 times as well. It will give a better response. We magnify both input and output by equal range. So this is our output now. This will give us some far better resolution. We then freeze it. After freezing it, we turn the timer on. We take B to the lowest value, and we want 0.169, that is something close to 0.17. So we take A to 0.1. Now we have a better resolution. This is 0.1. So we have 0.17 here. We take the time cursor and we place it exactly here. We can zoom it further for our benefit. So the time cursor is at 0.075. So this is our 63% value. The 60 that is our time constant by 63% method is 0.075. So tau CL practical is equal to 0.075. That is 75 millisecond. What is the tau CL theoretical? It would be, if you look at our time constant here, the time constant is 220 milliseconds. So our upper hand side here will have 220. 1 plus value of Kp is 0.92, if I am not wrong. I need to check again. The value of Kp is 0.92, and the last thing is Kc. If you look at it, the value of Kc is 2. So we'll have 0.92 into 2. So if we find it out, 220 divided by 1 plus 2 into 0.92, we get the value is equal to 77.46. So we see this value, which is the theoretical value, and this value, which is the practical value, they are almost equal. So we have found this to be equal for gain is equal to 2. We will have to see all the things. We have to find if these are equal for gain is equal to 1, 3, 4, 5, and 10 respectively. That is for you to do. And the last thing we require to do is closed loop, find out the closed loop frequency response. Closed loop frequency response is nothing, but it's just finding what we did in experiment 2. So in experiment 2, we used a wide range of frequencies, but in this case, we'll just take 1 Hertz. So we go to the setup. This is our setup. Level is 20%. Input is sine. Frequency is 1 Hertz. So we go here. Level is 20%. we turn the input into sine, and the frequency here it's rate. We can click here to change it to frequency, and we change it to 1 hertz. If you look at the right top corner, you'll see how it, if you look at the right top corner, you'll see how the velocity is shifting very fast. And you'll also see the effect of braking in here as well. Now, what happens is we have a sinusoidal input and we have a sinusoidal output. So what we'll do is we'll go to our data table, and in data table, what we do, we put k is equal to 1. Open loop phase lag at 1 hertz is the phase lag that at 1 hertz that we determined in experiment 2. We have that in the data table. The phase lag at 1 hertz, we'll write it here. So closed loop phase lag at k is equal to 1. What we do is, at first we turn k is equal to 1. After turning k is equal to 1, we freeze it. We turn the frequency on. We select D and find the peak. So this is 130, so phase lag is 40 degrees. Then we start again. Now the second data is k is equal to 5. Obviously, the data that I am taking will not be same as the data that you are taking, very obviously, because your value of kp time constant and ki will be different. You'll be using the same that you obtained in experiment that you used in experiment 1. So if we change the kc to 5, then what happens is we can see that our phase lag decreased to 15. So what we can observe is the more we increase the value of k, the more there is decrease in phase lag. That is a very important thing to observe. Another thing I would like to show you, I'll turn this into a step. Let's not magnify it, not magnify anything, and let's turn drive on. So the thing is, this brownish curve that you see is called drive. What does this drive do? This is very important. What this drive does is, you need to put a signal to in order to for these things to operate. That is, uh, suppose the voltage is turning abruptly from say minus 3 volts to 3 volts, suppose. So what you need to do is, when there is sudden change in voltage of the input, you want to change the output of the voltage, that is, you want to change the input of the motor abruptly to a very high level, so that it quickly reaches 3 volts. And after this 3 volts, you want to stabilize that value. You want to stabilize the output voltage. That is, there is a change in 6 volts here, right? There is a change in 6 volts from minus 3 to 3. So if the change is in minus 3 to 3, that is, if you across the motor, if you put a change in value of 6 volts, it will rise like this. But if across the motor you put a value of say 20 volts at first, it will quickly go to this place. It will quickly rise because it wants to reach 20 volts. Now, after it reaches a certain point, you decrease the input voltage, and so it becomes like this. So what happens is, what drive signals does is, drive signal does not increase the value of the drive signal does not increase the value of the output as the input provided. What it does is, it at first increases the value very quickly, and once it reaches something closer to our output steady state value, then it decreases the drive signal or decreases the change in voltage. For example, here you can see an abrupt change, the drive signal rises. It maintains a certain level. During that time, the output quickly increases in voltage or the velocity. Then it gradually decreases the drive signal. So this is the effect of drive signal. In the effect of observing this effect of drive signal, a phenomena comes which is called drive saturation, which is really important. Here you see that there is a flat peak at the drive. What this flat peak indicates is the system is 5 volt system. That is, it can either go to plus 5 volts or minus 5 volts. Now, if the system required to if the system was performing optimally, that is, if the output was reaching, output would have reached the input value at an optimum level, that is at a high speed. What would happen is we needed a drive signal that is much higher than 5 volts. Say about we needed a drive signal that was about 7 volts. But since the system cannot provide a 7 volt, what happens is it trims it down at 5 volts. And as a result, we see a flat peak at the drive signal. This is called drive saturation. This drive saturation occurs at high value of gains, and at high value of gains, because of this drive saturation, we will see that the experimental value, that is the measured value, will be different than the theoretical value. I don't know if these are shown different in simulation mode, but they might be different, and this difference is created because of drive saturation. If you decrease the value of k, you see, if you decrease the value of k, you see there is no flat peak because the drive can take a value lower than 5 volts in order to produce the same result. So this drive saturation occurs at higher value of gain, and because of this drive saturation, the experimental result or the measured result may or may not be equal to the theoretical result that we obtain. That is pretty much it for this experiment. And in the next experiment, we'll be learning about the behavior of the second order system. We'll be learning about overshoots and time of first peak, rise times, and everything that you'll learn in theory as well. That's all for now. Thank you.